So, eu ando muito.
Dá para começar aqui, entendeu?
Okay, so as we say usually, last but not least, the last speaker for this nice conference, but we will speak later. Last speaker, excuse me, will be Bruno Scárdua, da Universidade Federal do Rio de Janeiro, e ele vai falar sobre o teorema de Poincaré-Hopf para formas holomórficas. Obrigado.
Okay, thank you. It's my pleasure to close this meeting. And I'm going to talk about my work mainly with Professor Ito. Okay? I have to say that this work is highly motivated by questions very linked to the work of Professor Camacho, coming back to the year of 92. So, thank you for. Okay. This is not exactly a Poincaré-Hopf theorem. It's something like that for holomorphic one-forms. Okay? So, first of all, so this is my work with Professor Toshikazu Ito from Kyoto. Okay? So, first of all, I want to recall motivation for this work. basically, motivations, one motivation comes from the following well-known result for holomorphic vector fields in a neighborhood of the origin of C2. Okay, this is well known by you. I just have to recall. Okay, so you take an isolated singularity at the origin, and you say that the vector, the singularity is in the Poincaré domain if this matrix, the linear part, has eigenvalues lambda mu non-zero with quotient not a real negative number. Okay? So in this case, you say that singularity is in the Poincaré domain. We have a lot of work on analytical classification of this case. This is very well known, but I'm going to talk about some transversality property. So in this case, you have some other characterization which is as follows. So you suppose that you have an isolated singularity at the origin, and you have a linear part like this, quotient of eigenvalues non-real negative. You take a sphere, S3, small sphere, okay, small 3 sphere, and in this case, if the guy is in the Poincaré domain, then the vector field is transverse to these small spheres. Okay, so we have transversality of the vector field of this sphere. Of course, one first question would be, what about the converse of this fact? Okay, so about the converse, you have a theorem by Douadi and Ito, approximately 92, okay, which says that if you have, so I'm going to state it completely. Okay, if you have X holomorphic vector field in a neighborhood of the ball B2n 0R on Cn, excuse me, I'm beginning with the two-dimensional case, sorry, of B4 on C2, such that the vector field is transverse to the sphere, to the boundary sphere, then you have some facts. First of all, so you have this picture here, okay, for some ball. So first of all, you prove that the vector field, so I put this radius R0. So you prove that the guy is actually, there exists a unique singularity. Let me call this O. I can assume that this is the origin, okay? For the vector field inside the ball, only one singularity. This singularity is in the Poincaré domain. Indeed, so now I assume that the origin is the singularity. So indeed, the vector field is transverse to every sphere inside this ball center here. So if you have a picture like this, then you can find, if you have a picture like this, doesn't matter how big the sphere is, you can find only one singularity, okay, which is in the Poincaré domain So maybe I draw it as here. Okay. And the vector field is transverse to spheres closing up to the singularity. Okay. So this is a very interesting result, in my opinion, which is kind of a characterization of Poincaré type singularities in two-dimensional case. Okay. There are many other motivations for the question I'm going to propose, but this is one of them. Okay. I have to say that similar results were obtained by Alcides and Brunella, and Brunella himself. In this case, you consider boundaries of polydisk, of B-disk in the two-dimensional case. So you have a similar characterization of linear vector fields which are hyperbolic. They are transverse to the boundary of the B-disk, to any component of the boundary. And Brunella has studied what we call the Poincaré-Dulac case. Okay. So regarding spheres, okay, and making hypotheses on the flow on the sphere. Okay. So this two-dimensional case is very well studied. Okay, and these results are independent. You cannot take one from another. Well, one basic remark, is very well known by you, is that to consider foliations in the codimension one case, in neighborhoods of Stein domains of balls, for instance, is the same than considering vector fields in the two-dimensional case and holomorphic one forms in general. So when I talk about a vector field, I don't actually use the vector field. I use the foliation because any foliation in the neighborhood of the origin of C2 in the neighborhood of the ball is defined by a vector field. So it's the same thing. Okay? So I may write the word foliation here. If I want to regard, for instance, the codimension one case, I can consider foliations given by holomorphic one forms. There's no restriction, I mean, from the psychological point of view when you try to get generalizations of this result. Okay? So codimension one foliations, I mean, everything is holomorphic here, okay, are defined by holomorphic one forms. Of course, in neighborhoods of balls, okay, you have no cohomological obstruction. So I want to use this remark and motivate the question. Would be this one here. So, question or problem. Is there any codimension one holomorphic foliation F in a neighborhood of the ball B2N 0R on Cn such that F is transverse to the boundary sphere? I mean, of course, I'm going to assume that n is at least 3. So I'm not anymore on the two-dimensional case. Okay? So this is a question. And you don't know the answer. Okay? I mean me and Mr. Rito, we don't know the answer. Maybe it's well known. Okay? So very well. So I'm going to prove some results assuring that under certain conditions you cannot have this example. Okay? So first of all, I give you some, there are partial answers. Okay? You have some partial answers. So for instance, you can prove that in this case, F cannot be given by a homogeneous one form. This is using, I mean, this technique is going to appear here if you use Malgrange's theorem and things like that. Okay. Also, you can prove that F has no plane separatrix. I mean, you cannot have a separatrix which is smooth and intersecting the sphere because it's stability theorems like that. Okay, and you have no fibration of spheres over S2 and things like that. And using the things that you find, the features that you find inside Steenrod's book, you can prove that you cannot have F transverse to a sphere like a S4M plus 1. Okay. Okay. Well, so you have some restrictions on the integrable case. Okay. So in my talk, I'm going to talk about not necessarily about the integrable case. Okay. We have more cases to consider. So I must give some examples. Very simple examples. Okay, so some examples are like this one here. You take a look at C2M. So you are on even dimension. Okay, C2, C4, whatever. And you consider coordinates like Z2M. And you define omega naturally by, it's a kind of imitation of the radial vector field taking its dual. Okay. So this one for, if you take the radial vector field, of course this one form satisfies this identity here, and obviously the kernel of this one form, which is a distribution, singular only at the origin, the only singularity is the origin, is transverse to the sphere as for m minus 1. Okay, any sphere you want. Okay, but the problem is that when you work in higher dimension, I mean, I'm not on C2. It's easy to compute that omega is not integrable on form. There are more geometrical reasons, I'm going to show them. But omega, this guy here vanishes only at the origin. So in particular, it's highly non-integral. And actually, it's kind of related to the notion of contact structure. Okay, because you are taking things outside of the origin. So it's related to contact structures. Well, this is not the only example. Here you use the vector field, which is something that you already know, which is transverse to the sphere. So if you find something in the kernel, it's the one form is going to be transverse to the sphere. So playing with sums of radial and Poincaré-Hopf forms, you can find more examples. So I give you some kind of more or less general construction. Okay? So let's suppose you have a vector field transverse to the sphere. Okay? So I'm going to put S to n minus 1. I'm going to work on even dimension. Okay? Which is transverse to the sphere in the sense that you imagine. Okay? You just consider the distribution. Okay, so the plane that you find summed to the, I'm going to give the definition, but exactly natural definition, okay? In particular, the only simple remark I have to make is that here you are supposing that you have no singularities of the distribution on the sphere. Okay, so the singular set of the one form cannot meet the sphere, otherwise you can have many examples. Okay? So in this case here, if omega satisfies this and has no singularity on the sphere, then, of course, the kernel of omega, just the kernel, is transverse to the sphere. Okay? So you can actually construct vector fields like this by taking sums of two-dimensional things in independent variables. Now you see what I mean, no? So with this idea, you can consider, for instance, C given by, so you take here radial on x and y, for instance, no? So you are taking variables, for instance, on C4. You take now, for instance, Poincaré-Hopf on Z and W. So you can find forms, naturally given, that satisfy this thing here. They're not going to be integrable. I'm going to show this. But they are transverse to the sphere. So you can have other examples than this Hamiltonian here. Okay? Very well. So let me give the straight definition. So you take here omega holomorphic one form in an open subset U of Cn. You consider this, of course, given by the kernel of omega. Okay? And you give the definition as follows. You say that kernel of omega is transverse to N, a real submanifold of Cn, doesn't matter the dimension, if you have two things. First of all, the singular set of omega does not meet, I mean, this is interesting now in this case, of course, no? And also, you ask the kernel at any point plus, no? Not exactly like this. Of course, this as a real subspace. Of course. Okay? So this is a more natural definition of transversality you may have. This is the definition of transversality with foliation when omega is integral, of course. Okay? Well, so our main theorem would be like this. Okay, so you take, again, omega, holomorphic one form, in a neighborhood U of the ball B2N on Cn. Okay? Suppose that the kernel of omega is transverse to the boundary sphere. Okay? Then, you have two things. First of all, the dimension must be even. And second, there exists a unique singularity, 0 of omega inside the ball. This singularity must be simple. So you have only one singularity inside the ball, and the singularity must be simple. So any phenomena must happen in even dimension. Okay? This is the case of the ball. Of course, we have some generalization for the case of any domain with some hypothesis on the boundary and the Euler characteristic, of course. But this is most plastic one, clear. Okay? So what do I mean by a simple singularity? You write omega as Fj is J O n. This is holomorphic here. Okay? And you say that O in U is a simple singularity if, first, if it's a singularity, and, of course, it's a simple singularity of some vector field. Natural one is this guy here. Okay, so this is what happens. So this, in a certain sense, is related to the two-dimensional case. Okay? So this is our basic result. I'll give you an idea of how we prove this and how we play with these notions to obtain other things. Okay? So in general, we have something like you define the gradient of omega, which is inspired in the case omega is the differential of one form of some function. Okay, this is the infinite complex vector field grad of omega, defined by you take the complex conjugate of the coordinate functions and sum up. Sorry, this is a vector field. Let's go, it's fine. Okay. So this is a complex vector field of class infinity. It's no longer analytic. Okay. Of course, using this, you can define the index, which is not necessarily useful elsewhere, but here it's useful for us. You can define the index of omega. One remark is that my one form is not necessarily integrable. Okay, it's actually in the integrable case, this notion is not for isolated singularities in higher dimension. In the integrable case are given by Bourgogne's theorem, so they're not interesting from our point of view. So this is especially interesting in the non-integrable case. Anyway, this notion is useful in our proof. Okay, so you give another definition. You take isolated singularity of omega, which is also the same thing for grad of omega, and the index of omega at Q is, by definition, you take the index of grad of omega at Q. Okay? Using simple calculations, I think that if you have a dimension n, no, so it's minus 1 power n, the index of this holomorphic vector field here. Okay. So as you like, no? So let me write this. Omega is not necessarily integrable. Okay? So using this notion of index, you can state a more general version of this result using domains, no, and Euler characteristics. And the proof goes similarly. Okay? I'm not saying that we are making new definitions or whatever. I'm just putting on the blackboard the definitions we use. Okay? So let me give you one proposition, which is another way. Before even stating some more general version of the theorem, I'll give you an idea. I will give you a proposition saying that very hardly you are going to find integrable examples. Okay? So, and this proposition is interesting because it shows how we use techniques from several things. So you take omega, holomorphic, one form. Okay, omega, whose kernel is transverse, for instance, to the sphere, s to n minus 1. You already know that n is even, okay? Anyway, okay? Such that there exists holomorphic vector field, like for any example I have given. We assume that there exists a holomorphic vector field transverse to the sphere and belonging to the distribution given by omega. So this is a strong transversality hypothesis. Okay? So if n is 3 or bigger, then omega is not integrable. Okay, I mean, all examples we have constructed so far are not integrable, guys. And the reason is very simple. An idea of the proof. So we assume this condition here. We are on dimension 3 or higher. Okay? And take the sphere. And you take a look at the singular set of omega. So this singular set is an analytic set which does not touch the boundary of the ball. So it must have dimension 0. So this guy is discrete. It's finite set, actually. Indeed, by our theorem, it's just one point. Okay? It's some point Q. I mean, the intersection of this guy with the ball, no? But you don't have to use the theorem. You just have to use that the analytic set usually is going to touch the boundary of the ball. Otherwise, it must have dimension 0. Okay, this is a Stein property for, no? So you take one singularity here, and now you have an holomorphic vector field, which is by hypothesis transverse to the sphere. Explain the whole of the radial vector field in our first example. So this guy, by Eto's theorem with the G, proves, has one only singularity also inside the ball. Okay? And both singularities are simple. This is simple, Q1, and singularity of C is also simple, Q2. Okay? And also you have this condition here by hypothesis. So it's easy to prove that you must have the same singularity for them. The singularities must be the same, just using this formula here. So Q1 is equal to Q2. So you have just Q as a singularity. Now you apply Malgrange's theorem, saying that there exists a holomorphic first integral in a neighborhood of the origin. Some neighborhood here, there exists holomorphic in the integrable case. I mean, if you assume that omega is integrable, then by Malgrange's theorem, you must have holomorphic first integral in a neighborhood of the origin. So this is not compatible with this, because you find a function, f, and actually you must have df applied on C identically 0. So the singularity of this vector field is in the Poincaré domain. It's, for instance, and the radial, for instance, you can think of radial singularity. So you play with Laurent series. It's not possible. The only possibility is f must be constant. Okay? This is not possible to write for instance, for the radial vector field. Because it vanished at the origin. So you cannot have integrable case with this thing here. Holomorphic vector field in the kernel of the one form. Okay? In higher dimension. Okay? So I give you a short idea of the proof of the theorem. Just a warning. You can replace the ball by some domain, relative compact domain, and find some index result. Okay? I'm not going to write it down. So just one idea of the proof. Before, so we are essentially going toward the non-integrable case. So I have a proposal which is the one as follows. Take one non-integrable one form. So you have nothing to use as geometry in order to try to classify singularities of this object. So why don't we try to make some characterization by asking whether if it's transverse to sphere or not. This works on two-dimensional case. So if you go to C4, for instance, holomorphic one form, singularity at the origin, isolated singularity. So maybe you ask about tangencies with spheres or not. So in the non-tangent case, in the transverse case, what are the analytic models? Are these all the ones I have given here? I think that probably you're going to find this situation here, holomorphic vector field, in the kernel, transverse to the sphere. And of course, you can classify the vector field and come back to try to classify the one form, the contact structure at the end. Okay? So this is some kind of a sort of idea. Okay? So the idea of the proof is essentially the following. You take is the geometry of the gradient vector field. No? So if you take a point which is not a singularity of omega, okay? So you have something like this. You have the kernel of omega, codimension 1, complex subspace, and you have the gradient here. With this picture here, you would have the point P. Okay, so this is the basic picture we're going to exploit. Okay? So, what happens? I'm sorry, I have to rush right now. Okay? What happens when you have the sphere? So this is the sphere. Okay? So if P is not a tangent point, is a tangent point, for this and this. So you have something like, so this would be the kernel of omega. In the tangent points, I mean in general, and you have the gradient here, and also the radial vector field, so they are collinear. Okay? So this you use and make a combination of the gradient vector field and the radial vector field. I mean, in bad situations, they are collinear. So you use this and define, I'm sorry, I have just 5 minutes, I cannot give more details. There exists bump function Cn to R. So suppose omega is transverse to the sphere. Okay? So this is now my hypothesis. Just a remark there, and now my hypothesis. So there exists a bump function such that the vector field z given by grad of omega plus phi r, this vector field here is transverse to the sphere. This bump function is constructed as follows. You take a look at the analytic set given by Zj, Fj equal to 0. So this is analytic subset of Cn and contains the origin. So this guy is more or less like this. Okay? So you just, the bump function only exists in a neighborhood of this set. Just have to be careful here. Okay? Otherwise, the grad is already transverse to the, okay? So you just define actually phi here. Okay? With this, you are in the situation that you find some C-infinite complex vector field in a neighborhood of the origin. Excuse me. Which is transverse to the sphere. This vector field will give you the same singularities than the form omega. They will have the same singularities by construction of it. I can't detail this, I'm sorry. So what at the end you will obtain is using Poincaré-Hopf theorem to a real section of this vector field is something like okay, I mean you take one section, real section of this guy here. This is given by, first of all, you find real section here, and then you extend by homotopy. So you take one real section of this guy here, okay? And you just find one, which is the Euler characteristic of the ball, is equal to the sum of index of singularities of this guy. Okay? But the index, so now this, you use the relation between this and this vector field, which is essentially here. Singularities are just here. You can use this guy to calculate indexes. And what you find, as I showed at the beginning, is minus 1 and some number, which is the index of the holomorphic vector field associated to the one form. So Fj okay? So of course n must be even, so this disappears. Okay, because this is we know that this is holomorphic, so it's at least 1. Okay? And actually you only have one singularity of index 1, which is simple, so okay? So that's the main idea. And this is a very nice idea by Ito-san. Okay? So I'm out of time. I'm sorry. And I have to thank you for your attention. Thank you. Yeah.
Okay, so first of all, are there some questions, comments? Yes?
Excuse me? Yeah? The example I wrote? Yeah.
Differential is quadratic form.
Ah, yes. Exactly, yeah. I don't know. You know, this is a very interesting question. Actually, I think something like this. Because the only problem is that you can take a radial guy in x, y variables, and on z and w variables, some Poincaré-Hopf. Understand what I mean? Not just radial and radial in even dimension. So the resulting one form is not symplectic. I don't know. I don't think so. It has some degeneration, no? I don't know. It's symplectic anyway. If the answer is yes, so I think so. I think these are the only examples. Okay, I see. Tu pode former ela. Okay.
Another question, comment, observation, remark. Pop, 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 pop.
Ele go on.
Okay, so thanks again. So, eu acho que eu vou falar inglês porque